All right, so let me see if I can get this camera a little bit better. There we go. So what we're going to be looking at this week is some other applications of derivatives to the shapes of graphs and how this helps us with looking at certain types of problems called optimization problems, which are essentially when we're looking for how do we make something as big as possible or as small as possible. And of course, these are questions that come up all the time, right? We want to minimize the cost. We want to maximize the profits. We want to minimize the fuel expenditures. We want to maximize the lifespan of the machinery. All kinds of questions where we want to maximize or minimize things. We'll talk about more specific questions involving maximizing and minimizing in a bit, but what we want to do first is to just define some terms and then see how calculus can play a role. So the first thing that we are going to say is we want to look at maximums and minimums. And there are really two different types of maximums and minimums that we deal with in mathematics. So given a function f, we will say that f has a global maximum, capital M, if there is an x with f of x is equal to capital M, and for all x1, f of x1 is less than or equal to m. So the global maximum is the largest value that the function takes on. And global minimum is the same, but we'll write it with a little m if there is an x with f of x equals little m, and for any x1, f of x1 is bigger than or equal to little m. Now, these are the global maximums and the global minimums. And the thing about a global maximum and a global minimum is that functions don't have to have them. So I want to show you some situations where a function has them versus not having them. Just let's look at a few functions that we're familiar with. A lot of functions fail to have a global maximum or a global minimum. For instance, f of x equals x has no global maximum or minimum. And the reason for this is because this function gets arbitrarily large and it gets arbitrarily negative. So there's no biggest value that it takes on. There's also no smallest value that it takes on. Here's an example that has a global minimum, but no global maximum. So g of x equals x squared. This is going to have a global minimum at x equals 0, and the global minimum itself is 0 because the smallest value it takes on is 0, but it has no global maximum. And of course, we can think of examples that do in fact have both. For instance, h of x equals sine x. Well, this has a global maximum of 1 and a global minimum of negative 1. So the largest value that sine x takes on is going to be positive 1. The smallest value that it takes is negative 1. Now, an important result in mathematics is about when we can guarantee that there is a global maximum or minimum. And again, you don't necessarily always have them, as we saw in those examples. But there's only a few ways that things can kind of go wrong when we're talking about not having a maximum or a minimum. Like, one thing is you could just potentially grow without limit in both directions. So maybe you have a straight line like that, or you have something like this. Another thing that you could have is you're going along and you have some kind of a jump. And so this would end up having no global maximum, because even though it has an upper bound, it never has an actual maximal value here. So that would be another case where we don't get a maximal value. Well, it turns out that there are some circumstances where we can guarantee that there will be a maximal and a minimal value. And this is known as the extreme value theorem. The extreme value theorem states the following. If f is continuous on a closed interval from A to B, and it is very important that this is a closed interval. On an open interval, this doesn't work. And I will show you an example of why it doesn't work in a moment. If it is continuous on A to B, and A to B is closed, then f has a global maximum and minimum when we restrict it to the interval from A to B. Now, intuitively, the reason for this is the following. If I have a closed interval from A up to B, and my function is continuous, then I can't just go off to infinity up or down, because it would no longer be continuous. And also because this is a closed interval. So I have to actually hit my endpoints. But the only other way I could fail to achieve a maximum or minimum value is if I had a jump, and then I wouldn't be continuous anymore. So like maybe we reach a maximum here at some kind of a peak, and then we have a minimum at an endpoint, but we do have to have a maximum and a minimum. Now this isn't true if we go with an open interval A to B, because now I don't have to hit my endpoint, and I could climb up to some sort of a vertical asymptote at the endpoint. So in this case, I have a continuous function from on the interval A to B. It has no global minimum or maximum, but that's okay because this is an open interval A to B. This only works if we have a closed interval. Of course, maybe you have an open interval and a function that's not necessarily continuous, and you still have a maximum and a minimum. Like, that's perfectly possible. Maybe we just have this function here. This is not continuous, and it is defined on an open interval, but it does have a global maximum and a global minimum, because it literally just takes on these two values. So the bigger value is the maximum, the smaller value is the minimum. So this function, this theorem only works in the one direction. If it's continuous and the interval is closed, then we are guaranteed a global maximum and minimum. Now, the actual proof of this thing, I was trying to think if there was a good way to show you a proof of this. I really wanted to come up with a nice, simple sketch of what the proof looks like. Unfortunately, the proof is actually really, really technical. So I wasn't really able to think of a good way of explaining this proof that doesn't take us really far afield into various notions of continuity and things like that. So I'm going to kind of skip over it, but you can sort of intuitively see why it is true. The only way, if I have a closed interval, that I could fail to achieve a maximum or a minimum value would be if I jump around and therefore am no longer continuous. And if you're really interested in seeing a proof of this thing, then you can let me know and I'll direct you to where you can look at more information about it. The basic idea of it is you first of all observe that this thing has to be bounded, okay? And proving that is in and of itself a little bit of a tricky thing. But you prove that this thing has got to be bounded, and well, then you make use of the fact that there's a few different things you can do at this point, but one of the things that you can do is you can make use of the fact that continuous functions preserve limits. So essentially what you do is you choose a sequence of points such that their images are getting closer and closer to the least upper bound. And then you show, well, this sequence converges to some point, and the sequence of its images therefore has to converge to the maximum. That's one way of doing it. Another way of doing it is you prove something about compactness. So it turns out that the image of a closed interval under a continuous function has to be a closed interval. And therefore, it has to contain its least upper bound and its greatest lower bound. But again, that requires us to do some stuff about what is called compactness and, again, some rather technical things. So we're not going to get into it there, but I wanted to mention this. Now, there's another kind of maximum and minimum here that we want to be able to talk about, and that is going to help us to find global maximums and minimums as well. And this is the idea of the local maximum and minimum. So we will say that f has a local maximum, or respectively minimum, at x equals c if there is an interval, an open interval a to b containing c, and for any x excuse the ruckus in the hallway there, my apologies. They're moving some heavy stuff down the hall. But so for any x in this interval, f of x is less than or equal to f of c. Or respectively, for the minimum case, f of x is bigger than or equal to f of c. So what does this mean? Well, it means that we're not saying that this is where we globally achieve the maximum. What we're saying is that locally this is true. Now, what does locally mean? Well, locally means inside of some open interval around our point. Whenever we talk about a local property, we mean that in a small open interval around this point, we have this property. So that's what we mean by a local maximum or minimum at C, is that locally, this is the largest the function gets, is at C. Or locally, for the minimum, this is the smallest the function gets at C. Globally, it could be doing something totally different. For instance, if I give you this graph here, and I say this is y is equal to f of x, and let's say this is C1, C2, and C3, then this has a local minimum at x equals C1 and C3, and a local maximum at x equals C2. Now, globally, of course, it gets much bigger than it does at C2, because, of course, this goes up in both directions towards infinity. But on some open interval near C2, it achieves a peak at C2. And around C1, it achieves locally a minimum, because near C1, it's bigger on both sides. So this is the idea of having a local maximum or minimum. And usually with the global maximum or minimum, it's all about the image. It's all about the y value. What do you get from the function? This is the largest the function ever gets. For local maximums and minimums, though, it's all about where it happens. Now, we might also ask, what is the y coordinate when we achieve this local minimum or when we achieve this local maximum? But primarily, it is about where it happens along the x-axis, which it might help if I actually labeled the axes, but you probably knew which I was talking about. Now, let's take a quick look here at sort of how you can get a local maximum or a local minimum. And I want you to actually, after I draw a couple of these, I'm going to ask you to pause your video for a bit and just draw some examples out of your own head of local maximums and minimums. And I want you to think about a question, which I will tell you in a moment. But here's some examples of local maximums. The pictures that we get. So maybe we have something like this, where I have like just this nice smooth curve that comes over in this bump shape. And similarly, for a local minimum, I might have something like this. You know, it's a nice smooth curve. It just comes down in this little dip and it comes back up. Another possibility is maybe I've got something that comes to a sharp point, or maybe I have something that comes to sort of like a cusp. Same sort of thing down here. And then I could have something maybe that jumps around a bit. Like maybe I come up like this and then it jumps down like so. Well, this would still be a local maximum. And this would still be a local minimum, even with this jump. Now, look at these 4 examples. And thinking about where the maximum and the minimum happen, what can we say about the derivative at that point? There's actually 2 possibilities that we see in these examples. Sorry, the sunlight is being very annoying today in terms of making the board look funny. So there's actually 2 different possible things that we see happen to the derivative here. Can you see what they are? So the first one is going to be, in these cases, it looks like the derivative should be 0 because we've actually got a horizontal tangent line there. And in these other cases, it looks like there's no derivative at all. The derivative is undefined. Now take a minute, try to draw and think about some additional ways in which you can get a local maximum and minimum, and see what you say about the derivative there. Okay, so I hope you were able to come up with a few different examples. They probably all looked something similar to these. We've kind of drawn all the possibilities for local maximums and minimums that I can think of anyway. And the thing to observe is that it looks like if x equals c has a local maximum or minimum, then f prime of c is equal to 0 or is undefined. Now, if you think about it, intuitively that makes a lot of sense. If I am at a local minimum, I should either be swapping from decreasing to increasing or swapping from increasing to decreasing, depending upon whether we're talking about minimums or maximums. And either way, I should be going from something that's sloping in one direction to sloping in the other direction. How is that possible? Well, either the derivative is going to have to cross through 0, or the derivative is going to have to be undefined because it's jumping around. And so this leads us to a couple of, to an important theorem, but before I can state the theorem, I got to give you a couple pieces of terminology. So the first thing is that if x equals c is a local maximum or minimum, we call it a local extremum. So extremum just means maximum or minimum. We're not interested in which one it is. It's one of the two. And the other thing that I want to say is that if x equals c, or let me write it this way, if at x equals c, f prime of c equals 0, or f prime of c is undefined, we say c is a critical point for f. So, places where the derivative of a function is undefined or 0 are called critical points. Now, our observation that it looks like if we have a local maximum or minimum, the derivative is 0 or undefined, can now be summarized by saying if x equals c is a local extremum, x equals c is a critical point for our function. This is what we expect to be true. And it is, in fact, true. So let's see how we can prove it. So proof. And let's suppose x equals c is a local maximum. If it's a local minimum, we just are going to get the same thing, but all the signs are going to be reversed. So if we can take care of the local maximum case, the local minimum case is easy. It's exactly the same argument. So I'm just going to do the maximum case, and we're not going to worry about the minimum case. Then what are we going to be able to say? Well, first of all, if f prime of c exists, then here's what we know. Consider the limit as h goes to 0 from the right of f of c plus h minus f of c divided by h. Now, because this is a local maximum, f of c plus h for small values of h is going to have to be smaller than f of c, or less than or equal to f of c. Therefore, this is going to be a less than or equal to 0 number divided by a positive number. And so this is going to be the limit of a bunch of numbers that are either negative or 0. Well, if this thing here is less than or equal to 0, then its limit has to be less than or equal to 0 as well. However, the limit as h goes to 0 from the left of f of c plus h minus f of c divided by h, this is going to have to be bigger than or equal to 0. Why? Because we have the same thing. We have that f of c plus h is smaller or equal to f of c, but now h is negative. So this time we have a negative over a negative, which is positive. Or maybe we get 0. If I have an expression that is always positive or 0, then its limit has to be positive or 0 as well. Now, if f prime of c exists, then these two limits have to exist and they have to be equal. But the only way that these two one-sided limits could be equal is if they were both 0. So they must both be 0, and f prime of c is equal to 0. And that completes my proof, because if the derivative exists, it has to be 0. If the derivative doesn't exist, well, then it's a critical point, because the derivative not existing makes it a critical point. So we can find all the local extremes, all the local extrema, by finding the critical points and then checking, is this in fact a local extrema? Now we got to be careful because the answer is not always. So notice all local extrema occur at critical points, which I'm going to abbreviate with CP, but not all critical points have local extrema. So let's look at a couple of examples of this sort of thing. Here is one example. So let's look at f of x is equal to 2 times x minus 3 squared. Well, f prime of x is always defined, and it's going to equal 4 times x minus 3. If I set 4 times x minus 3 equal to 0, this has the solution x equals 3. So this is my only critical point for this f. And this is, in fact, a local minimum, as we can check pretty quickly, right? We can see that this has to be a local minimum because, well, amongst other things, we know that this is a parabola, and therefore that on either side, this, we can see that f of 3 is equal to 0, and f of x is bigger than 0 when x is not equal to 3. So actually, we can see that this is a local minimum. So this time we've got a critical point and it corresponds to a local minimum. But sometimes you can have a critical point that doesn't correspond to a local extreme at all. And a good example of this is g of x equals x cubed. Well, in this case, g prime of x always exists and is equal to 3x squared. If I set 3x squared equal to 0, I get x equals 0. But notice that this does not actually correspond to a local maximum or minimum. And why not? Well, look at what's happening here. The picture that we get is this when I graph it. So you notice that if I'm to the left of 0, my function is smaller, but if I go to the right of 0, my function is bigger. This is not actually a local maximum or minimum. So what we have is this is a critical point, but not a local extremum. What's really going on here is, yes, we have a horizontal tangent at this point, but we bend over, touch the horizontal tangent, and then immediately start going back up again. So you cannot just say, here's a critical point, I must have a local extremum. Now, the nice thing though is that if you want to find all of your local extrema, then all you got to do is find your critical points, and then you test each critical point to see whether it is a local extremum or not. And the simplest way of doing that, or not necessarily the simplest in the sense of easiest, but the simplest in the sense of the most direct, you just jump right in and ask yourself, near this point, can we show that this is a minimal value or a maximal value? But there are other more clever ways of trying to figure out whether it's a local minimum or maximum that can be much easier in a lot of situations. So we're going to end up talking about that in a little bit. The one other thing I want to observe here is, how does this connect back to the global maximums and the global minimums? So notice that if f has a global maximum or minimum, it occurs at an endpoint. Let's say if f is continuous, because we also have to take into account discontinuities. So if there's discontinuities, then, well, actually, that's taking care of business. So we can drop that, because if it has a discontinuity, all discontinuities are critical points. At an endpoint of the domain, or at a critical point. So if I have a function defined on some interval and I want to see whether I can find the global maximum or minimum, one way of doing it is just find all the critical points inside of that interval and then just evaluate the function at the endpoints and at the critical points. And that is going to give me a list of values. The largest of those values is my global maximum, and the smallest of those values is my global minimum. As an example of this, if I want to find the global maximum and minimum for f of x is equal to, let's say, -4 times x minus 2 squared plus 3. Well, I can look, and let's say that we are doing this on the interval from 0 up to 6. Well, I can say f prime of x is equal to -8 times x minus 2, set -8 times x minus 2 equal to 0, and we get x equals 2. That is our only critical point. It is indeed in the interval from 0 to 6, so it is relevant to our question here. If this critical point weren't inside the interval, then we could just ignore it. Or maybe we get some additional critical points outside of this interval. Again, we just ignore them. But in this case, it's inside the interval, so we're okay. So then we just do f of 0, well, that's equal to 3. F evaluated at, or I'm sorry, it's not equal to 3. I am being silly here. It's going to be negative 4 times 4, so negative 16 plus 3, it's negative 13. F of 2, this is what's going to be equal to 3. And then f of 6, this is going to be 4 cubed is 64, so negative 64 plus 3 is negative 61. So this is my global maximum, and this is my global minimum. And there we go. We found the global maximum and the global minimum this way. Now, what we're going to do next time, we'll look at some slightly more complicated functions and things, and then we will also talk more about how do you find these local maximums and minimums and verify whether they are local maximums or minimums. Because notice that in doing this procedure, I don't need to find whether I have a local maximum or minimum. I'm just saying, hey, it occurs at a critical point. We're just going to list all the possible values and then go from there to find the largest value and the smallest value. But sometimes we are actually interested in finding local maximums and minimums as well, not just the global ones. So that is something that we're going to have to do. However, I'm going to stop things here for today because I have been delayed today and I'm running a bit late. So we will come back and pick up more examples next time.